everyone, this is a quick proof about the weak law of large numbers. Now, I've already done a proof for the weak law of large numbers, but in the previous proof that I did, we used Chebyshev's theorem or equation, and we assumed that the variance of the random variables was finite. In this particular proof, we actually assume nothing about the variance, so it doesn't have to be finite. And this proof is a little bit more robust. It is also a little bit more involved, and we're going to need to know two facts that you might not know off the top of your head. And those two facts are the Taylor series approximation for a function when it is n times differentiable, and this other fact where we have a sequence of elements an that converge to a, then we have the limit as n goes to infinity, 1 plus an over n, all to the power of n will go to e to the power of a. And that's what this notation means. It essentially just means e to the power of a. So to prove that this property up here is true, which is essentially the weak law of large numbers, where we have a sequence of random variables all with the same finite mean, then the sample mean will converge to the true mean. So that is essentially the, in probability, that is essentially the weak law of large numbers when we're not assuming anything about the variance. So to prove this, we're going to use characteristic functions. Now, the characteristic function of a random variable, which is just the sum of other random variables, ends up being the product of the characteristic functions for that random variable. Now, this all of these x's are distributed the same. So, well, first let me say, by the definition of the characteristic function, this is e to the power of it xi, which is equal to e it x all to the power times n, and this is just for any arbitrary xi. So I dropped the I because this is for any arbitrary x, and we're assuming all of the x's are distributed the same. Now, we actually don't want to know the characteristic function of s sub n. We want to know the characteristic function of Sn divided by n, which ends up, we just can add this divided by n over everything to get that, and that's just a property of characteristic functions. So now we want to approximate this guy over here. It's not necessarily an easy task, so what we're going to do is use that Taylor series approximation. Now, we know that the first derivative exists because we have a finite mean, and that is a property of characteristic functions and moment generating functions. And we also know, so the first element is at k equals 0. So approximating this, we have 1 plus expected value of x it over, oh, let me erase this, it divided by n to the power of 1 over 1 factorial plus o t to the power of n to the 1 power. And we still have that n, the n power over here, and that comes over. The reason why we can do this is because at k equals 0, f to the 0th derivative evaluated ends up just being 1, and then 0 factorial is just 1, x minus, or this would be it minus 0 ends up being, to the power of 0 ends up being 1, which is how we get 1 here. Similarly, we find the expected value of x as the characteristic function, the first derivative of the characteristic function evaluated at 0, and so forth. We don't add any other elements because we only know that the mean exists. Now we can take the limit of this So we have the limit as the characteristic function Sn over n t as n goes to infinity, and the limit of this other side. Now, this particular property is using little o notation, and if you're not familiar with that, I encourage you to pause the video and double check how that works. But essentially, as n goes to infinity, this property goes to 0. So we're only going to worry about this term up here. Then we have that this is going to be approximated by exp to the power of it times the expected value of x. This n actually goes down to the denominator. We ignore the 1 factorial, so that's all we have to worry about. Now this ends up being e to the power of it times mu, which is the characteristic function of a degenerate random variable, which means that Sn over n converges in probability to mu.